Okay, so hello and welcome back. So in the previous video we worked all the way up to question number 7, and one of the things that happened in the few previous videos was that one of my videos unfortunately got lost for whatever reason. I don't have the video anymore, and so about an hour or so of video is just simply not there, and it's somewhere between the somewhere related to question probably number 5 or 6 or something like that. If that happens to be important, please feel free to ask questions, and then I will try to answer specific questions. Otherwise, I don't really know what the contents of that video were, and if it happens to be important, then please let me know. So question number 8 we have, let star be the binary operation on n defined by a star b is the HCF of a and b, and is star commutative, is star associative, does there exist identity for this binary operation on n? So the question is that the star is a binary operation on the set of natural numbers n, and defined by basically a star b is equal to the HCF of a and b, the HCF of a and b. Now the questions that we want to answer is number 1 is star commutative, and number 2 is star associative, and number 3 is there an identity for this binary operation, an identity for this binary operation on n. Now, in order to answer this question, so first you need to understand what is the HCF of two numbers. And in order to understand that, basically, you know that the HCF is basically nothing but the highest common factor. HCF is nothing but the highest common factor. Right? And so the HCF is the highest common factor, and so let me give you an example. So for example, let's say that you have a 12 and some other number like 18, right? So 12 is nothing but basically, you can write it as 2 times 2 times 3, right? And 18 is the same thing as basically 6 times 3 is equal to 18. So that's 3 times 2 times 3. That's 2 times 3 times 3, right? So what that means is that now each of these numbers that you can see over here. So when you basically, this is the prime factorization of 12, this is the prime factorization of 18, meaning that you write basically 12 as, for example, when you prime factorize it, you use that prime factorization tree, and then you write 2 times, for example, 6, and 6 is 2 times 3, and therefore 12 is the same thing as 2 times 2 times 3. So this is called the prime factorization of 12, which is of course very helpful in many types of situations. This is related to class 6, or class, I suppose class 6, but one of the most fundamental things in mathematics. Anybody that has anything to do with mathematics has to understand it properly. And so this is the prime factorization of 12, this is the prime factorization of 18. And so basically what happens is that now you can already see that basically there are, and each of these numbers is called a factor of these numbers. So for example, you would say that basically 12 has two factors of 2 and a factor of 3, or 18 has one factor of 2 and two factors of 3, and so on and so forth. So now you can see that basically there is a common factor of 2 between these two numbers. There is also a common factor of 3 between the two numbers, but then 2 and 3 are not common, so you cannot basically count them as common factors. And therefore, based on this, you can say that the HCF of basically 12 and 18 is the same thing as, so here basically the common factor is 2 times, yeah, it has to be multiplied, times basically the other common factor, which is equal to 3, which is 2 times 3 is equal to 6, right? Now 2 times 3 is equal to 6, so then you can say that the HCF of 12 and 18 is equal to 6. Now you can see that basically 12 is divisible by 6, meaning that 12 divided by 6 is equal to 2, remainder 0. And 18 is also divisible by 6. 18 divided by 6 is equal to 3, remainder 0. And of course you know that basically, since each of these numbers is divisible by the HCF of the two numbers, then of course those numbers are greater than or equal to this number over here, because they are actually multiples of this number, and this number is one of the factors of any of these two numbers. So however you want to talk about it, of course you can. So there are a few things that here you need to understand. Generally, there is basically something called a factor. There is something called a multiple. There is something called the HCF, and there is also the concept of divisibility, and so on and so forth. But hopefully you have learned all of them in class 6, so you have no problem here. But usually people forget what is HCF and LCM, so I had to talk about this here, right? So that means that basically the HCF of basically these two numbers is 6, and then you have to basically pay attention to how basically I found the HCF of the two numbers, meaning that I prime factorize the number, and I prime factorize this number as well, and then whichever factors are basically common between the two numbers, I take those factors and multiply them together, and that becomes the HCF of those two numbers, right? So that's basically the concept of HCF, right? Now, coming back to the question that we had here, basically we said that star is a binary operation on the set of natural numbers, and defined by A star B is equal to the HCF of A and B, right? So now you want to answer the question, is the star commutative? So star is commutative. So basically we said that a binary operation is commutative if so the condition for commutativity, so the condition for commutativity was that for every A and B belonging to, for example, let's say to A, let's call the generally we can call this set A. For every A and B belonging to A star B is equal to B star A. If that is the case, then you can say that basically star is a commutative binary operation. Now over here you can see that basically the HCF of A of basically you can say that in this particular case, basically A star B is equal to the HCF of A and B, and basically B star A is equal to the HCF of B and A, right? So of course you can, based on how we found the HCF of those two numbers, and of course it has to be, of course, it needs to be proved. I mean, naturally it needs to be proved mathematically, but let's assume that we have proved this mathematically, that basically I can say that since we know that basically the HCF of A and B is equal to the HCF of B and A for every A and B belonging to the set of real numbers at least. And of course then the set of natural numbers is just a subset of the set of real numbers. So then we can say that basically therefore basically A star B is equal to B star A, and therefore star is commutative. And therefore star is commutative, right? So that's one part of the question. Now, in order to basically answer the part whether star is associative, we need to consider the condition for basically associativity. For associativity of star, let's say, and that is basically for all A, B, and C belonging, let's say, to A, to some general set, for example, to some general set A, then basically A star B star C is supposed to be equal to A star B star C, right? And you can write this way and this way, so both ways they have to be equal. And let me write this. A star B star C is equal to A star B star C. Now this is again something that of course you need to prove mathematically, but again we are assuming that you have proved this, or you are assuming that somebody has proved this, and then you have read the proof and understood it and it's logical and there is no problem with it, and so now you are basically using that proof here. Otherwise you cannot just write something in when you're basically doing mathematics. Of course everything has to be proved, and of course you might actually think intuitively that something is true, but then if you try to prove it, either in some cases either you cannot prove it, or then you will come to the logical conclusion that what you thought was true is actually not true. So you need to be careful with intuition. Intuition is sometimes a little bit tricky. So what this means is that then the condition for associativity, then now what this means is that now I can examine the two parts of this equation. Okay, so now I have to go back a little bit. I did actually make a very bad mistake here. It was a logical mistake that I made here. Okay, so then basically you naturally, of course, you need to examine each part of this equation and see if they are the same. So in this particular case, so a star b star c is the same thing as now a star b, as we know from here, is basically the HCF of a and b, right? So this is the HCF of a and b, and that star c. Now this is the same, so this becomes the same thing as basically the HCF of basically the HCF of a and b and c, right? So that is that. Now, so the HCF of a and b is going to be basically some number. It's going to be some number, for example, call it d or whatever you want to call it. And then basically then you have another number over here, c, and then you're taking the HCF of those two numbers. Now, in the world of HCF, of course, this is what I was talking about. This is what you need to basically prove. Otherwise, you cannot use it in algebra. But this is actually equal to the HCF of A, B, and C. Meaning that if you prove this, you will get this. And as I looked at the solution here, I saw that basically they have made the assumption that this thing has been proved, so they have just simply used it in the solution without even talking about it. But I mean, I've never actually seen in these books, that in the NCERT books, that these have been proved. Some things are in these books are just simply assumed, and that's of course the case with many things in mathematics. It's just not possible to prove everything. Otherwise, you would end up instead of learning mathematics, you would end up proving things which, of course, it doesn't make much sense. So some things, of course, you prove, some things you don't prove. You have to do it in such a way that you do that while you are learning mathematics, and that's basically what these NCERT books actually do for you. So now the other part of this equation is basically A star, B star C, which is the same thing as A star, and B star C is basically the HCF of B and C, right? And then A star that is the same thing as the HCF of A and the HCF of B and C, right? Now, the HCF of B and C is going to be, well, some number, right? And then there is also A as well over there. And then you're taking the HCF of these two numbers, of one number over here, one number over here. So this is going to be equal to the HCF of A, B, and C, right? So you can see that basically these two expressions are both equal to the HCF of A, B, and C, and therefore you can say that basically the A star B star C is the same thing as A star B star C, right? And therefore star is associative. So now that's another part of this question that we answered. So this was that. Now the next part of this question is there an identity for this binary operation on N? Now remember that the identity was basically E, which is basically the for the definition for the identity that we talked about was that so the definition for the identity was that basically given a binary operation star on a set A, an element E belonging to A, if it exists, is called the identity for the operation star. If A star E is equal to E is equal to A is equal to E star A. So what this means is that basically suppose that you have some binary operation star on a set A. Suppose that you have this binary operation on the set A. So then in this case, some element E. So an element E belonging to A, belonging to the same set, if it exists, is called identity for the operation star. Is called identity for the operation star. For the operation star, if basically if A star E is equal to E star A is equal to A, right? And of course that is for all A belonging to A, right? So that means that basically all of the elements of the set A, if you take basically A star E and if you take E star A, in both cases you have to get back A, and that is basically for all elements of the set capital A, right? So basically what this means is that you have to, in this particular case, which we were talking about, the HCF of basically two numbers A and B, and we are talking here about the set of natural numbers. That means that in the set of natural numbers, you have to find an element that basically meaning that, so you can say that in this particular case, you have to find some element E belonging to N such that basically A star E is equal to E star A is equal to A for all A belonging to N. In other words, A star E would be the HCF of A and E must be equal to the HCF of E and A. That must be equal to A for all A belonging to N, right? Of course, this part is not a problem because star is basically commutative, so the HCF of A and E and the HCF of E and A are basically equal in the first place, so we have no problem with that. But then the problem is that the HCF of those two numbers has to be basically the HCF of the identity with any number that you take in the set of natural numbers has to be the same number that you take in the set of natural numbers, no matter what number you take in the set of natural numbers. And then it has to also cover all of the numbers in the set of natural numbers, meaning that if this relationship is not valid even for one number in the set of natural numbers, then you cannot call that E, you cannot call it the identity for the operation star, right? So that's basically the condition. So now let's investigate this a little bit. And basically the way that you can investigate, usually you can start from, for example, when you're talking about the set of natural numbers, you can start from 1. 1 basically belongs to the set of natural numbers. Basically the HCF of 1 with the HCF of, we know that basically the HCF of 1 and 1 is the same thing as 1, right? So I can now take one of these numbers as E, take one of the other number as A, for example, and continue with this investigation. Now, suppose that, for example, I have the HCF of, for example, 2 and 1. The HCF of 2 and 1 is again equal to 1, right? And the HCF of, for example, 3 and 1 is again the same thing as 1, and so on and so forth. And of course, over here, basically, I got 1 over here I have no problem. But then over here, I'm supposed to get 2. Over here, I'm supposed to get the 3, and so on and so forth. So basically, what that means is that 1 as the identity is not working here. Now, another way to investigate this is to find at least 2 numbers, any 2 numbers in the set of natural numbers, in the case of which basically take one as the identity and take the other one as A, and so what that means is that when you pick those two numbers, the highest common factor of those two numbers has to be equal to A, basically. So you have an A and you have an E, and you're taking the HCF of these two. The highest common factor of those two of these two numbers in every case has to be equal to A. And let me think about this. Okay, so I think I found a better way to think about this, but still it's not a perfect way. But still it's better than basically than what I proposed before. So basically you have two numbers that you need to take into consideration. You have your A and you have your E, right? And you're taking the HCF of these two numbers. So you can start with, for example, a 1 and a 1, right? And you take the HCF of, for example, a 1 and a 1 is equal to 1. So then you have no problem. You're supposed to get your A back. You can take your A as basically one of these ones, and then the other one you can take it as E, and so you can then assume that basically E can be equal to 1, and you have no problem with E is equal to 1. But then this E has to work for all the other members of the set of natural numbers. Then if you take, for example, the HCF of 1 and 2, then the problem is that then still you'll get a 1, right? And since I'm changing these numbers to change my A and not E, and I'm keeping my E constant, now I'm taking this number as E, I'm taking this number as A, and so I didn't get my A back, right? So here I have a problem, which means that E cannot be equal to 1. So E as E equal to 1 is not right. It's false. I cannot take E is equal to 1. I can look for some other number, meaning that, for example, then I can look for E is equal to 2, right? And then see if basically 2 works with basically all the members of the natural numbers, meaning that, for example, I can take of course 2 doesn't work with any of the members. Even if you start with a 1, the HCF of, for example, 1 and 2 is equal to 1, and so it doesn't work here either, and so 2 is just simply ruled out. So then you can go for 3, and then you can go for 4 and 5 and 6 and so on and so forth. And it seems that this number is basically the identity for this binary operation in the set of natural numbers cannot simply be found. And I'm saying this based on what I can see in the solution. Otherwise, my logic is not wrong, but it's not all inclusive. You basically, if you want to use this logic as a proof, it has to be something that can actually be logically used in a proof. So then you have to make some changes to the logic so that it can basically prove everything, or for all of the elements in the set of natural numbers. I'm not sure what sort of logic I would use here in order to check all of the numbers in the set of natural numbers in the case of, for example, finding the HCF of these two numbers and find that number, but then it seems that the number can simply not be found, so we call it basically we answer the question as no and then simply move on, because then it's just simply not we don't have to spend more time on this anymore. I mean, we have already answered the question. And just let me take a in the solution, the way that they have answered the question is that now an element E belonging to n will be the identity for the operation star if A star E is equal to A is equal to A is equal to E star A for all A belonging to n. But this relation is not true for any A belonging to n. Thus the operation star does not have any identity in n or on n. So that's basically how they have solved the problem, but they have not basically proved anything. They have just stated some. They have just stated you could call it only the answer. Otherwise, the proof is not there. So that's basically that, and it's not really economical to get more to spend any more time on these problems. As long as you understand really what is, for example, what is the identity, the concept of identity, then you can leave the problem alone. And of course, if such a thing is asked in an examination, then you can use you can answer the question in the same way. You would probably get all the marks that you need to get for that question. And at this point in time, basically at this level, you're not supposed to actually prove that basically the answer is true, but then mathematically speaking, this is not the right way to answer a question. Of course, it has to be a logical proof, which it is not, but it's not a problem for now. Okay, so that was question number 8. Question number 9 is, let star be a binary operation on the set Q of rational numbers as follows. Find which of the binary operations are commutative and which are associative. So suppose that you have this is question number 9, and you have basically some basically binary operation on the set Q, and as follows. Okay, so now suppose that basically part 1 of this question is that basically A star B is equal to A minus B. Now the question that you want to answer is whether star is commutative or associative. Of course, basically star is not commutative because A minus B is not equal to B minus A. So about basically for being commutative, you know that basically if basically A star B is equal to B star A is equal to B star A for all A and B belonging to the set of rational numbers Q. If that's the case, then basically you can say that then star is commutative, right? So that is basically the condition. Now you know that basically A star B, you know that A star B in this particular case is equal to A minus B, and you know that B star A is equal to B minus A, and A minus B is not equal to B minus A in the case of basically in the case of these rational numbers. Of course, for example, suppose that you have you take A is equal to, for example, 2 and B is equal to 3. then basically 2 minus 3 is equal to negative 1, and 3 minus 2 is equal to 1. And of course 1 is not equal to negative 1. Therefore a minus b is not equal to b minus a. And for basically you can say for all elements of all a and b belonging to the set of basically rational numbers, and therefore a star b is not equal to b star a. A star b is not equal to b star a, and therefore basically star is not commutative. Star is not commutative. Now, about star being associative, so then you can say that basically if a star b star c is equal to a star b star c, and you can write this way, and you can write this way for all a, b, and c belonging to the set of basically rational numbers, then you can say that, for example, star is associative, right? Then star is associative. Now, so now basically we need to examine both sides of this equation and see if they are actually the same in this particular case. So then a star b star c is the same thing as basically we said that a star b is equal to a minus b, right? So that means that over here I can write a minus b star c, and so that's the same thing as basically a minus b minus c, right? So that's a minus b minus c. On the other hand, a star b star c is the same thing as a star, and b star c is the same thing as b minus c, right? Now again, a star, this whole thing, is the same thing as a minus this whole thing, a minus b minus c, which is the same thing as a minus b plus c. And of course, basically a minus b minus c is not equal to a minus b plus c, and therefore a star b star c is not equal to a star b star c. And you can write it this way, and you can write this way. And I would say for all elements, for all a and b and c belonging to Q, although I'm not really sure about this part, but it doesn't really matter whether it's for all elements or for, even if for one element it's not the same, then of course this condition is true, and then there is no problem with that. And then of course you can generate at least many counter examples to show that basically this is actually the case, and therefore you can say that basically star is not associative. Star is not associative. So that was basically part 1 of this question number 9. And And basically what they have done in the solution, they have used numbers. I have used algebra here. Algebra is simpler than numbers because in the case of numbers you have to think a lot in order to find a couple of numbers that basically that you can use in that particular case. But then when you use algebra, you can simply write everything in using variables, and then it's the whole thing becomes much easier and much simpler. So that's basically how they have done it. Okay, so part 2 of this question is again the same question. Basically, star is a binary operation on the set Q, and basically this time basically part 2 of the question is basically a star b is equal to a squared plus b squared. A squared plus b squared. Okay, so again, I wrote the conditions here up here, so you're already familiar with the conditions. I'm just going to simply talk about the solution. I'm not most probably not even not going to write it down because it's going to take a long time in order to write these down. But for the most part, I'm just going to talk. So a star b is equal to a squared plus b squared. Now, if I can show that basically a star b is equal to b star a for all a and b belonging to Q, then that means that basically then star is commutative, right? Of course, then whenever you're of course, normally what you have to do, you have to write this statement that basically if this is the case, then for example, then star is commutative. Then star is commutative. So I do suggest that you write your statements this way. If you know what you're doing, I mean, if you're working on something that you're familiar with, then you can write your statements in any way that you want. You can even do them in your head. It's your own choice. But if you're not well familiar with what you're doing, I do even recommend that you write your statements this way, because when you write them this way, you will understand them much better, and then there is no room for making mistakes, right? But then now, for the sake of, in the interest of time and other considerations, I'm not going to write everything down that meticulously. But then, of course, the way that you write your mathematics has to be elegant, and it has to be written in such a way that people understand it. Meaning that it's not supposed to be ambiguous. So that's the main point. Meaning that when I write, for example, if a star b is equal to b star a for all a and b belonging to Q, then star is commutative, then there is no ambiguity there. Everybody would understand this. But then if I simply write a star b is equal to b star a for all a b belonging to Q, this statement, this doesn't mean anything. Basically, this statement it does of course mean something. What it means is that a star b is equal to b star a for all a and b belonging to Q. That means that what this means is that basically this basically is already the case. That means that we have shown that this is already the case. But what we want to do is that we want to actually examine whether this is the case or not. right? But as long as I mean, there is a voiceover over this video, then there is those problems don't exist. But suppose that you are writing something down in an examination, or you are basically working on some problem on your own. Suppose that you are a mathematician, or you're writing a paper, or you're writing down some mathematics for some other person. Then in that sort of case, basically, if you write this statement instead of this statements, these are actually not the same things. They don't mean the same thing. So you have to be careful about that. Okay, so now basically what we have is that if A star B is equal to B star A for all A and B belonging to Q, then star is commutative. So we already know that. So then we need to see if that is the case, if this is the case in the case of in this particular case. So then A star B is equal to basically A squared plus B squared, right? A squared plus B squared. And also B star A is the same thing as again the same thing as well, it's the same thing as B squared plus A squared. And of course, you know that basically addition is commutative in the case of rational numbers, and therefore you can say that basically A squared plus B squared is equal to B squared plus A squared, and therefore basically A star B is the same thing as B star A, and therefore basically star is commutative. And therefore star is commutative, right? So that's basically one part of the question. Another part of the question is that you want to know whether star is associative. Basically, to check that, you can say that basically if, and of course you have to be, your writing has to be neat and clean. So I don't need to basically, you already know how to write your things down, but and I'm not trying to set an example here of anything, but well, your writing has to be organized, neat, clean. Those types of things you already, hopefully, of course, know. So now basically you can say that if A star B star C is equal to A star B star C, and you can write this way, and you can write this way for all A, B, and C belonging to Q, then basically, or as a general condition, you can just call this set, you can call it A, for example, belonging to A. Then you can say that star is associative. So this is just a general condition in the case of a general set A. So now again, you need to basically examine each part of this equation separately and see if they are the same. So A star B star C is the same thing as basically A squared plus B squared star C, right? And that's the same thing as basically this whole thing. Basically we know that A star B is equal to A squared plus B squared. That means that you take this number, raise it to the second power, take the second number, raise it to the second power, and add them together. So I have to take this whole thing, a squared plus b squared, raise the whole thing to the second power, and add to that, and basically raise this to the second power, and add to that, right? Which is the same thing as basically, this is the same thing as a plus b whole squared, which is a squared plus a plus b whole squared is the same thing as a squared plus 2ab plus b squared, right? So that's a squared raised to the second power is a raised to the power 4 plus b raised to the power 4 plus 2 times a squared b squared plus c squared, right? So that's basically a star b star c. Now, a star b star c is the same thing as basically of course you have to examine this part first, so you write this as a star. Now b star c is the same thing as b squared plus c squared based on this. So this is the same thing as b squared plus c squared. And now a star, this whole thing over here is the same thing as basically you raise this to the second power and add to that, and raise this also to the second power and add to that. So b squared plus c squared raised to the second power, which is the same thing as basically a squared plus b raised to the power 4 plus c raised to the power 4 plus 2 times b raised to the power 2 c raised to the power 2, right? And of course you can see that this is absolutely not the same thing, meaning that basically based on this you can say that basically a star b star c is not the same thing as a star b star c, and therefore basically star is not associative. Therefore star is not associative. Again, over there they have used numbers, but I personally use algebra whenever I can. It's not possible for me to use algebra all the time because there are some parts in mathematics. I mean, algebra, you can use it wherever you know how to use it. There are many parts in mathematics I don't know how to, I do not really know how to use algebra there, so I cannot use algebra there. But basically this algebra is as I have probably said before as well, it's one of the most amazing tools that I've seen in my life. It's actually a very it's just the most mysterious thing that I have seen in my life. It's like it has a life of its own, and it connects everything together. It's a wonderful tool, really. So, but again, over there in the solution they have used numbers instead of algebra. You can pick your own way of solving the problem. That's up to you. So in the next video we will continue with basically the rest of these problems. I'll see you in the next video, and thank you.